Kekule suggested this structure for benzene, and that's that structure with 3 localised pi bonds and 3 regular carbon-carbon single bonds. Benzene is now represented by this structure, which is a picture of cyclohexane but with a pi ring in it. Figure 3 shows the relative stability of the current structure versus Kekule's structure. And then our question says, use figure 3 and the data shown in table 1 to calculate delta H2. So I'm going to go back to figure 3. Obviously you can see both the data on the table when you have your exam paper open in front of you and figure 3. So I'm not going to keep flicking backwards and forwards, but I am using the data in the table. So we're being asked to calculate delta H2. We can see that we've been given delta H1, which looks like it's the enthalpy of formation of the modern structure that we're using for benzene. What's happening in the third arrow up on the left-hand side, we can see is that the Kekule structure, which if we remember has a C at each of these points, and each one of these has a H atom, hydrogen atom, attached. And then we can see it's been turned into 6 gas carbon atoms and 6 gas hydrogen atoms. So what that means is we're literally pulling apart that structure, we're breaking every bond. So we can see that we're breaking 3 CC single bonds, so that's 3 3,4,8s, 3 CC double bonds, 3 6,1,2s, and 6 CH bonds, so 6 4,1,2s. So if we add all that up, this arrow is 5,352. On the right hand side, we're turning 6 carbon solids into 6 carbon gases. So that is 6 lots of atomization. The enthalpy change when 1 mole of gaseous atoms is formed from the element. And then it is 6 lots, because we're turning 3 H2 gases into 6 hydrogen gas atoms. So the enthalpy of atomization is the enthalpy change when 1 mole of gaseous atoms. So we're forming 6 moles of hydrogen atoms. So we can add this side up, and we could get 5,598. So according to Hess's law, enthalpy change is independent of root. We want delta H2. So there's a couple of ways you could do this. If you look at this diagram, there's sort of an obvious vector kind of quantity to it to say that the left-hand side and the right-hand side must be equal. So you could do it this way, plus delta H2 plus 83. And if you rearrange that, you would get that delta H2 equals 5,352 plus 83 minus 5,598 minus delta H2, because I've moved delta H2 over to the left hand side. And then that, if you rearrange that, that gives you delta H2 is 163. So you could do it that way, or if you want to use Hess's law, you could say that the arrow delta H2 starts here and ends here, and so the other route would be all the way around like this. So delta H2 equals minus 83 down that first arrow, plus 5,598 minus 5,352, and you would get the same answer of 163. So if I just go over to the space for that, I can write my answer on the line, 163 kilojoules per mole. Explain in terms of structure and bonding why this structure with the pi bond is thermodynamically more stable than this one with the localised pi bond. So this with the ring. And that is because the electrons are delocalised. This is localised pi bonding. And this is delocalised. And so because those electrons are more spread out, there's more stability. A mixture of concentrated nitric acid and concentrated sulfuric acid react with benzene. Figure 4 shows the incomplete mechanism. Name the mechanism. So the mechanism for the reaction with benzene is called electrophilic, because we're using an electron pair donor, acceptor. Substitution, because we're swapping a H for a group. Complete the mechanism by adding any lone pairs. 2 curly arrows to step 1, a curly arrow to step 2, a curly arrow to step 3, and a curly arrow to step 4. So 4 curly arrows altogether and any lone pairs. So it's kind of a spot the difference game. Some of this mechanism parts you will know, and some will be unfamiliar. So if we go down to step 3, probably all familiar that you have from the pi bond to the electrophile, to the end with the positive charge, and then in step 4, you reform the pi bond by substituting off the H. So probably all familiar with those 2 bits, and there's no lone pairs to add. If we go back to the beginning, this is an unfamiliar bit, so it's kind of spot the difference. So if we look from the beginning to the end, we can see that this bond here has been broken, and then a new bond has been formed here. So there must be some lone pairs on this oxygen, and one of them has gone off to fetch this hydrogen to form this new bond, and we need to break this OH bond and put the electrons onto the oxygen so the oxygen becomes negative. And we'll do the same thing in the next one. We can see that the difference is we've broken this bond here, and so we're going to take this bond, and we can notice that the nitrogen becomes positive and the oxygen becomes neutral, so the electrons must move towards the oxygen to get rid of the plus on the oxygen and to leave a plus on the nitrogen. So we can add that curly arrow as well.